All right, everyone. So now remember, the big finding from the last video was that change in V over V equals F over 4 times epsilon 1 minus epsilon 2 minus epsilon 3 plus epsilon 4 in that standard configuration, where, again, we have here, 1, 2, 3, 4. So remember that. Keep us in standard configuration, and let's go ahead and look at an example. So let's look at a quarter bridge configuration. A quarter bridge, only one strain gauge in our bridge. That's actually epsilon 1 here. We're pulling in that stress in the 1, 1. So we know there's no strain gauge here, here. So 2, 3, and 4 are 0. So we're just going to be basically pulling. Now, that epsilon 1, 1 is only going to be a function of, remember, 1 over E, 1, 1 minus nu sigma 2, 2 plus sigma 3, 3. So those are both dead. So basically, we end up with this relationship. So we're only pulling. There's no bending going on. So it's only basically tension, axially. So we're only pulling essentially in that direction. So that is essentially the strain that we'll be measuring for that strain gauge 1. Now, let's go to another scenario. What about if I'm doing this here now? So same idea. I only have one, so it's a quarter bridge configuration, but now we have stress in the 1, 1, stress in the 2, 2. So my strain in the 1, 1, which again, it's only measuring that strain in the 1, 1, but now it's going to not only account for, you'll see that the strain in the 1, 1 is going to account for the stress applied here and the stress applied here. So depending on the magnitude, who knows, those values can change. So remember, it's always 1 over E, sigma 1, 1 minus nu, sigma 2, 2, plus sigma 3, 3. So this is now not 0, so this is 0, so the full expression will be this. So you have to make sure to kind of see where that strain gauge is going. It's not just, what is contributing essentially to that strain measurement. So be careful. What about here? So now we have what's called a half bridge configuration. So now we have strain 1, strain 2 right here. So what's going to happen is 3 and 4 are 0. You still have now this same relationship for strain 1, 1, but now you also have this relationship for strain the 2, 2, where now if this pulls, now this is getting extended positive, or, well, they're all positive because the strain here is in tension. But now depending on the magnitude, essentially those values can change. So again, this will feed into here, this will feed into here. So epsilon 1 equals this, epsilon 2 is equal to epsilon 2, 2. So you have to feed that into the expression depending on what the parameters of the problem are. Fantastic. You can kind of see that here. What if we're doing a cantilever beam? Kind of a classical example. Now we're no longer bending, or we're no longer doing axial. It's basically pure bending here. Now, is there some axial strain? Probably some, but it's going to be somewhat negligible. Only one strain gauge, dead. And now we're just going to have this one here. Is the bending strain going to be positive or negative? And then what I do is, when we're doing bending, this is top. So if this line is solid, if it's dashed, that means it's on the bottom. So if I'm bending in this scenario, basically the beam is going to be elongating, right? So this strain of bending will indeed be positive. Now that's going to come out essentially in the wash, but important to kind of understand. Actually, it's very important to understand basically as you're calculating and figuring out essentially that strain and seeing how the material stress behaves as well. This is one scenario for beam bending, and you can actually calculate it out explicitly. But if you're in a cantilever beam scenario, I'm just going to kind of skip ahead just slightly. Depending on the location, this is essentially what your equation is going to look like, where D is essentially the distance from the load that's applied to here, length of your system, et cetera, et cetera. B, H, so width, H is your height. So this is an equation to memorize. You can absolutely calculate it like we've done previously, where it's E dot I dot Y quadruple prime equals Q of X. And I may ask you to do that. No, we'll see. It's always possible, but this is a good equation to memorize. I might not be too. I had my chance to investigate your knowledge and material, so we don't need to go through again. Excellent. Now, let's go through here. Let's look at this scenario now. I have a strain gauge here strain gauge 1, strain gauge 4. I'm bending the same way. So now this is positive bending. 2 and 3 are gone because they're not, here. And now I have a strain in the 4 direction, and the 4 is being compressed. So it's the same bending if it's in the same location. And that's kind of what I'm trying to kind of show here, like that they're all at the same distances. But now this is negative. So I'm going to end up with a scenario where this is going to be 0, right? This bending calculates this bending out. So putting the strain gauge, right, in the particular positions really matters. So you really have to be aware of that when you're connecting your Wheatstone bridge. You can unintentionally connect the Wheatstone bridge, and I did it in our lab, where you cancel out that voltage and it's not changing. Same thing with when you're trying to apply, when you're trying to amplify the signal as well, potentially. Now, strain is important. Thermal strain. Thermal strain exists, right? In our strain expression, epsilon 1, 1, there is, if there's a change in temperature, sigma 2, 2 plus sigma 3, 3 plus alpha delta T. So there will be a thermal requirement in essentially the strain that you're measuring, potentially. So if you're in a quarter bridge configuration, you're also measuring a contribution that's thermal strain. So regardless of what this is, and it may be much larger, but you're still getting some of this contribution. So sometimes you want to be able, and you want to make sure to kind of negate that. So if I wanted to, in this particular example, right, this is going to cancel out basically everything except this bending gets cancels out this. And what you're left with is actually 2 alpha delta T here. So actually here you'd only be measuring thermal strain potentially. But if I wanted to make sure that I wanted to measure bending purely and eliminate thermal strain, you can do E1 and E2 on the bottom, right? Or actually, yeah, E2 on the bottom, and then you'd be left with basically 2 E bending. Does that make sense? Yeah. So I'm in pure lecture mode now. Excellent. Now before we get into some worked examples, and some other kind of, combined loading states, we're going to talk about calibration, and one kind of really cool way to do a shunt calibration for your strain gauges. And we'll get into that next time, and then we'll get into some more complex loading states. So, but this is a good kind of crash course into how do you convert change in voltage to strains and how you want to write out some of these problems. So we'll see you next time. Thanks. Bye.